You know that moment you flip a light switch? We just see instant light, right? But in the world of electricity, there's this hidden drama, a whole story that unfolds in that split second. So today, let's pull back the curtain and take a look at that secret life. It really seems like it should be simple. Off becomes on, 0 becomes 1. But is that change truly 100% instant? Well, as you've probably guessed, the answer is no. The thing we see as instantaneous is actually a process, a tiny little journey from one state to the next. And this isn't just about your bedroom lamp. This little transition period, it happens in every single electrical circuit out there. We're talking about the massive power grids that light up entire cities, all the way down to the microscopic circuits inside the phone you might be holding in your hand right now. So let's dive into this moment of change. The world of electronics actually has a specific name for this period, and believe it or not, understanding it is absolutely critical to making all of our modern technology work. It's called the transient response. It's a fancy-sounding term, but all it really means is how a circuit behaves as it's moving from one stable condition, like off, to another stable condition, like on. It's that in-between time, and that's where all the really interesting stuff happens. Now, to understand this whole story, we've got to meet the characters. Every circuit is made up of different components, and 3 of the big ones are the resistor, the inductor, and the capacitor. And the best way to think about them is that they each have their own unique personality. First up, we've got the resistor. This one is the most straightforward, predictable character in our little drama. Its job is simple. It resists the flow of electricity. It's consistent, it's steady. You can pretty much just think of it as electrical friction. Okay, now let's meet our main character for today, the inductor. Its whole personality, its entire reason for being, is built on one simple idea. It absolutely hates sudden change. The one rule it lives by is that the current flowing through it can never change in an instant. It will fight with everything it has to keep things stable. And that one rule, that's the key to this whole story. And just real quick, let's meet the inductor's cousin, the capacitor. It's kind of similar, but with a twist. While the inductor fights changes in current, the capacitor fights changes in voltage. It's like a tiny, super fast battery, storing and releasing energy to smooth things out. Okay, so we've met our players. The stage is set. Now it's time for some action. It's time to actually flip that switch and see what our main character, the inductor, does when it's faced with the one thing in the world it can't stand: change. So here's our setup. It's about as simple as it gets. We've got a power source over on the left, an open switch at the top, and there's our star, the inductor, on the right. Right now, nothing's happening. The circuit is off, 0 current is flowing, everything is perfectly stable. And click, right at this moment, which we'll call time equals 0, that switch closes. The power source is now connected, and it wants to blast current through the circuit immediately. But guess who's standing in the way? Our inductor. This is it. This is where it all happens. You've got the power source demanding an instant rush of current. But then you've got the inductor, with its deep-seated hatred of change, putting up a massive fight. What happens next is basically an electrical tug-of-war. Whoa, okay, don't panic when you see this slide. I know it's a lot of math. Physicists have written out the script for this whole electrical drama, and this formula is basically it. But look, we're not here to solve equations, we're here for the story. So let's just forget the symbols for a second and focus on what this thing actually looks like in real life. And here it is. This one graph explains the entire concept perfectly. Instead of the current shooting straight up from 0 to its max value, like you might expect, look at that beautiful curve. The current grows gradually. That gentle slope, that is the inductor, in action, pushing back against that sudden change and forcing the current to build up slowly. It's not a jump, it's a slow rush. Now, check this out, because this is where we see both sides of the story. On the left, that's the current we just talked about, slowly rising. But on the right, that's the inductor's protest, which we measure as voltage. At the exact moment the switch closes, the inductor is freaking out, so its protest is at its absolute loudest maximum voltage. But as the current slowly settles into its new routine, the inductor starts to calm down, and its protest just fades away to nothing. So this slow rush is happening. But how long does it actually take? Are we talking a microsecond, a nanosecond? Well, engineers have a really clever, specific way to measure how long this whole transition period lasts. It's called the time constant. You can think of it as the official unit of measurement for this transition. Now, for reasons that are buried deep in the math of exponential curves, one time constant is officially the time it takes for the current to get to exactly 63.2% of its final value. Yeah, I know, it's a weirdly specific number, but it gives engineers a consistent milestone to work with. And this table here really shows you the whole journey. After that first time constant, boom, we're already over halfway there at 63.2%. After the second one, we're up to 86%. But notice how each step gets us closer, but the jumps get smaller and smaller. By the time 5 of these time constants have gone by, we're at 99.3%. I mean, that's so close to 100% that for all practical purposes, we can say the drama is over. The circuit has reached its new steady state. So why does any of this matter? Why care about this microscopic tug of war? Well, because that slow rush is actually a feature, not a bug. Engineers use this effect to protect the super-sensitive chips in your phone from a sudden jolt of electricity that could fry them. They use it to smoothly manage power across national grids. They even use that predictable delay to build the little timing circuits that count down the seconds on your microwave or your toaster. Mastering this split-second transient, it's everything. So the next time you flip a switch, just for a second, remember that tiny hidden process that's making it all possible. And it kind of makes you wonder, right? What other things in our lives that we see as totally instant are actually a beautiful, gradual process, if we just look closely enough.